All right. All right. Good afternoon, everybody. We are Group One. My name is Bruno. I am the project lead. We have John, our test pilot. Prajakta, she's our fuselage engineer. Riley, he's doing structures. And we have Kayla, which is doing aerodynamics. So next slide, if possible, Professor. So let's start with the design process. This is our plane, no collar on, so you guys can see the full geometry. It looks nicer this way for the geometry. So the design concept of our aircraft took inspiration from the glider AE324. It's a commercial glider. It's used for leisure, and it just looks really nice. So we took some of the characteristics from it for our final design. We took the design of a single seater. It has a thin tail fuselage, a very thin tail fuselage, and a very large V-tail area compared to the horizontal tail. And for our project, we decided that the best way to do it was to incorporate everything into one Excel sheet. So we made a couple calculators that we could use to calculate the weight and the center of gravity all in one sheet. So all we needed to do was to add the chord length, the wingspan, horizontal tail area, vertical tail area, and then everything else is generated for us. We played a little bit with those numbers, and we found our best and most efficient design. Next slide. All right, now projector. You first.
Hello guys. So in order to make the fuselage more aerodynamic, we took the fuselage frontal area 30% of the wingspan. All right. Can you hear me now? Okay. The fuselage frontal area we took 30% of wingspan, and the coefficient of fuselage drag is calculated according to the formula given in the uh, project. And then fuselage diameter is 2.2, and its length is 22.5.
All right, now let's scale it.
Okay, for the portion of the X-plane design, wing aerodynamics, the horizontal and vertical tails in the wing and the X-plane were designed using knowledge learned in this class and trial and error. We based the chord length and the wingspan off of research done on the ETA glider, a German Italian open-class self-launching glider manufactured by the ETA aircraft, and adjusted our values according to attributes of our own glider. Through trial and error, chord length was chosen to be 2.5 feet and wingspan to be 75 feet to cause the plane to fly more efficiently and fly further. From solving the equation of wingspan is equal to the wing area over the chord length, we calculated the wing area to be 187.5 feet squared. Next, we used our wingspan and wing area to calculate the aspect ratio, where the aspect ratio was equal to the wingspan squared over the wing area, and we found that the aspect ratio was 30. Having the largest aspect ratio allows the gliders to have a greater coefficient of lift and to fly longer distances. Lastly, through trial and error, our horizontal and vertical tail areas were chosen to be 8 feet and 3 feet to get us to the center of gravity that would let the plane be stable during the flight.
All right, now it's Riley.
Hello, I'm Riley Olson. I was in charge of structures and weight. The main problem I had when we started, the plane weighed about 4,400 pounds, so I got to tell a lot of people no. After that, basically, we just created an Excel sheet with the dimensions for all of our wings, and we played with sizes until we got to about 3,700 pounds and got coefficients that we liked. After that, I was also in charge of C of G. Right now, the pilot and the C of G are right on top of each other. That's just a coincidence. I don't know how that happened. I'm sorry. But She does have a little bit of a nose down tendency. I worked very long to try and get it to the state where it is now, but that's the only major issue I've found.
John, our pilot.
So I did everything else anybody else did. I took the instruments that we were given from the sheet. The three that I thought that were the most important was the artificial horizon, the airspeed indicator, and the altitude indicator. I did also use the smaller altitude indicator because I didn't think we needed one so big. But those three were the most important. Mostly anything else on there I thought was not very useful. I mean, I can kind of tell which way I'm leaning, left or right, and also the artificial horizon also tells me that. I also put some other random things on the right, flare button, other things, just for shits and giggles. But other than that, I mean, that's pretty much all that's with the dash, not anything fancy.
All right, next slide. So now let's talk about specs and performance. So our airplane has a wingspan of 75 feet, chord length of 2.5 feet, wing area 187.5 feet squared, aspect ratio of 30, fuselage length 22.5 feet, fuselage diameter of 2.2 feet. That means the pilot has to be almost laid down on the chair. It works, all right, it works. Horizontal tail area is 8 feet, vertical tail area 3 feet. Those were explained. We had to fiddle with those to make the CG work. And our final weight with the pilot in is 3,840.5 pounds. And so for performance, we calculated that our airplane is most efficient at 100 feet per second. It can fly up to 350 seconds when it's up to that speed at an angle of 1.6 degrees above horizon. Now, we decided not to only focus on time aloft. We decided to also focus on CL over CD versus velocity. So what we did is we plotted two graphs and we found both peaks. Anything in between here is the most efficient flight you can have for the plane. Anything that's above about 35 lift over drag ratio. Our plane can maintain that for a long time, and we can keep in flight for more than 350 seconds if we keep right in the middle here. And that's about it. Thank you. What? Oh, you were supposed to talk about it. What's up? Because during trial and error, we found out that the plane could maintain its altitude at level flight for longer if you focused on CL over CD. So it worked better for us. I don't have the exact mathematics on it, but when we were test flying, it flew for a lot longer than 350 seconds. Anyone else? All right. Here you go, Professor. Thanks. Yeah.
All right. So this is our AE324 design project. If you want to go to the next slide. So a quick overview of the project. We want to increase the time aloft of our aircraft as much as possible. Some of the fixed variables that we had for this project included an initial height, an initial velocity, a maximum weight, and a wing efficiency factor. So we kind of had to work around all these different things that way that we could get the best time aloft possible and keep our aircraft in the air. Go to the next slide. So a quick overview of our team members. I'm Ramses. I'm the team captain and design lead. This is John. He's the wing aerodynamics and X-plane wing developer. This is Sergio Kisaka. He's the fuselage designer and painter. That's Jackson. He's the structures lead and weight and balance coordinator. This is Weston. He's the pilot and cockpit designer. And that's Jasper, and he's like the performance calculator. Next slide. You go, John.
All right. My name is John Lamb, and I was the one that did the wing aerodynamics and X-plane design. So first we started off by getting areas for the vertical and horizontal tail. Basically, how we did that, we did a market study of various gliders with certain with the similar gliders to see what estimate we would want for the wings for the horizontal and vertical tail. And so basically we had to keep our tails low, overall size of our tails low, as they would make the plane unstable relative to the CG. And basically part of my calculations correlated with the person that came up with the CG location. They'll be discussed later on in this presentation. But I was working together with the structures person trying to figure out a good CG location. You can go to the next slide. So basically, we had two airfoils that we were given, the NACA 0009 and NACA 0006 airfoils. They're both rectangular symmetrical airfoils. And from our research, we did various calculations on Excel to figure out, or not various calculations. First, we looked at the airfoils to see how they were different. And from that, we determined that the 0006 airfoil had a lower coefficient of drag. And our main goal was to get a higher CLCD value. And so that's why we chose the 0006 airfoil, because it had a lower coefficient of drag. We basically compared between the two at an angle of attack of 0 degrees. And you can go ahead and go to the next slide. Here's the 0009 airfoil, and you go next slide.
Hello, my name is Sergio Kasaka, and I was in charge of the drag coefficient calculations, the fuselage. Oh, can you hear me now? Oh. All right, so my name is Sergio Kasaka, and I was in charge of the drag coefficient calculations and the fuselage design along with the paint scheme. So in order to design our fuselage, we needed a drag coefficient. In order to get the drag coefficient, we needed to get the dimensions of the diameter and the length of the fuselage. So for the diameter, we measured our 6'6" pilot with a tape measure while seated down, and we were comfortable with a 4-foot diameter, and we all agreed that that would be the best diameter for our pilot to be seated comfortably aboard the airplane. We decided on the length of the fuselage based on the low coefficient of drag. Since we already determined the diameter, we used the calculation from the equation that was given to us on the handout to solve for the length. So we set the drag coefficient equal to 0 and took the derivative of that equation and solved for the length that would turn out to be 16.73 feet. So we use the same formula to calculate the drag coefficient based on the frontal area of the fuselage, and we got a drag coefficient of 0.1346 that we included in our body data under X-plane. We then solved for the drag coefficient based on the wing area, along with the wing area and the area of the fuselage, and we got a value of 0.00721. Next slide. For our fuselage design, we looked at a couple gliders for inspiration, and we found a way to approach the design by using 13 stations and edited each cross-section station accordingly and to get a shape that we desired. Next slide. So this is the view of our fuselage design. That's the top view, that's the bottom view, and that's the side view. Next slide. And that's the front and the back view. Next slide. For our paint scheme, we use the Photoshop app to sketch a new design for a glider prototype. And we chose this unique colorway because we thought it would be different and not an ordinary design that you usually see on our gliders. Next slide. I was responsible for the structures. So first I started with the viewpoint of the pilot, which I'd put 3.5 feet back because our pilot has long legs. And then I put it roughly 5 inches from the top so that he'd have a seat and wouldn't hit his head. I had to adjust the wing and tail placements in order to figure out the best center of gravity. So I had to work with John a little bit there in order to figure out the right areas and placement for the plane to be stable in flight. I designed originally 3 wheels for the landing gear, and changed it to 2 because most gliders online only had 2, one right below the right in front of the width of the fuselage and right at the end of the fuselage. And then I based the control geometry off of the glider example in class with some minor adjustments to make it easier for our pilot to fly. Next slide. Our overall weight was 2,760 pounds. We had it at a higher weight, but the center of gravity was giving us some issues and making the flight unstable in X-plane. So we had to make adjustments resulting in a lesser weight. And the aspect ratio has a very large role in the center of gravity as well as the weight. So the wing plays the largest part. And like I talked about earlier, I had to work with John in order to get the right center of gravity in front of the quarter weight for the wing. That's it. Next slide. Yeah.
All right, ladies and gentlemen, this is your captain speaking. So I was chosen as a pilot for 2 reasons. I went to a Huntsville space camp in high school. It was at the U.S. National Space and Rocket campus. And I was mainly in the control center, mission control. But during the scuba part, I was unable to because I have a seizure condition. So I went and did a flight simulator instead. So I already had some practice with it. And due to my epileptic seizures, I will never be able to fly a plane in my life. So this was a very good chance for me to at least like the closest thing possible. So I'd like to give a thank you to my group members for agreeing with letting me do this. So the piloting was composed of 3 stages. The initial flights were just using the simulation glider from X-Plane 9 and just to get the hang of it. And then we had the trials, which is just troubleshooting our glider. The main problem we had was our center of gravity. Like we would immediately drop out of the sky and start spinning. We got that all figured out though, luckily. Third step was just practice, practice, practice. Need multiple satisfactory flights. And for the next couple days, I will also be in here continuing to practice. Next slide, please. So the cockpit design, we only have 4 instruments because I whittled them down until I finally figured out what I actually needed. So we just have the airspeed indicator. It starts out at 100 knots is what the simulation is to my knowledge. So we have a good indicator for that. We have the artificial horizon, which also has the angle of attack built in, which I found to be very helpful. 2 birds with 1 stone. I chose radar altitude because it shows how high up from the ground. Normally this could be a problem, but considering this is Kansas and everything's flat, we had no problem at all with that. And of course the timer just to make it easier within the simulation. Next slide, please. All right. All right.
Okay, so I was the part of the fun part of the calculations for performance. So we started by getting our CRs and CDs in line. Then we did some calculations with most of the calculations were given to us in class and over the textbook. We just plugged them in and gathered all the information from there. Once we got the CD and CL sorted, we just got glide ratio and the glide angle from that, and all the calculations just came from that. Next slide. All right. So here is our time aloft. Our maximum time aloft falls at around 50 knots, which gives us around 312 seconds. This is an important part of the glider. It's mostly based on the multiple things that the wingspan, the length of the wingspan and the chord length. Keeping the weight below 4,000 pounds, we were way below that. And the goal was to get the maximum time aloft. All right, next slide. So here are some other charts that shows CL versus CD. And we got L over D versus velocity, then glide ratio versus velocity. All right, thank you. Next slide.
So to recap all of our plane stuff, our time aloft that we ended up getting was around 313 seconds. Our weight was about 2,760 pounds. Our aspect ratio was around 17.62, which I think makes sense because the bigger aspect ratio you get, the more like insane structures you're gonna need to maintain that wing. And our total range was around 26,000 feet out from when you start. So you go to the next slide. And here are some pictures of our plane. You can kind of see the front design that Kisaka put on there. And we wanted to, add the cool teeth because we thought it looked unique and we liked that on fighter jets and stuff like that. So that's why we named our plane the F-04 Super Wasp, because if you put thrusters on that thing, it would basically be a jet. So yeah, that's our plane. And then next slide is questions. Any questions? Beautiful. Yep.
Missing today, so we're gonna go at that. You guys fantastic. All right, guys. Thank you for sitting in. We're gonna introduce you to the Endurance 8 by Group 3 WES. Next slide, please. So we'll start off by meeting the team. Next slide, please. Kyle and Dolphy, you're our wings guy. What year are you, Kyle? I'm a junior. You're a junior. What brought you to aerospace? We're going to go to planes for everything in the air. Speak up that way. Just so they can hear you. Why did you choose to be the team's wing aerodynamics lead?
Well, to be honest, I kind of got into the divvying up the jobs pretty late, so I didn't have many jobs left. But I jumped into the aerodynamics lead because I wanted to work more with the mathematics side of things, because that seemed to be the part that I excelled at in class.
Fantastic. Next slide, please. Next, we're going to introduce Pierce White, our fuselage guy. What year are you, Pierce?
I'm a junior.
What brought you to aerospace?
Well, I just like spaceships and aircraft.
Why did you choose to be the team's fuselage design?
Because I feel like it being very sleek, I put the fuselage and really.
Fantastic. Next slide, please. Oliver Price, structures. This is our structures guy that is missing today, so we're going to skip past this. No surprise. Bob Ross. Sorry about that. He's our ace. What year are you, Bob?
I'm a junior.
What brought you to aerospace?
I'll be a test pilot and I need an engineering degree to go to test pilot school, so I decided to go to aerospace.
Why did you choose to be the team pilot?
Because I'm a certified private pilot.
Are you nervous to fly for us on Friday?
No.
Fantastic. Next slide, please. Mohammed Rashid, performance. What year are you, Mohammed?
New York.
What brought you to aerospace? you choose to construct the performance data analysis. Good calculation, fantastic. Next slide, please. Angel Santana, the captain. I'm a junior. I chose aerospace because I was a student pilot for a time, and I had a lot of questions that didn't make any sense. So I wanted to learn a little bit, and actually I answered all my questions here in this class. Thank you, Dr. Smith. Why am I the team captain? Well, in all honesty, I'm leaving aerospace after this semester because I have no more questions left. And I told the team to pick out their favorite position, and I'll take what's left over. So, yeah, next slide, please. Let's get started. Our goal as a team, we wanted to create a glider with a thin and long profile. Having long and thin wings, we believe that we can create a glider to outfly our competitors. Our fuselage also remains small as we leave very little surface area for the relative landing. Next slide, please. Our wing aerodynamics. Our goal. Our wings should be long and thin. Our wings should be structurally sound, and our wings should be short enough to stay within the 4,000-pound limitation. Our fuselage goal. The fuselage should be very compact and reduce drag. The fuselage should be streamlined, and the fuselage should be large enough to fit our tall pilot. All right, so here's came up with. We have a super long wing with a super long thin fuselage, just what the doctor ordered. All right, here, this is our fuselage here. I'll let Pierce explain what's going on.
Okay, so my goal is trying to make it very sleek and like that, not too heavy, like 4,000 pounds. And so and at the same time I had to make it so it can still fit our pilot. So I tried to make it as small as possible, and it ended up being like 2 foot wide and 3 foot tall, the biggest part. And then it just spins out from there. And then overall, it's all 3 foot long. And so it's very like long at the end.
The wings.
So when designing the wings, the first question we had to answer was whether we were going to use the 009 or 006 airfoil. And we ended up going with 009 only because it seemed to be better geared towards a lighter style plane, in our case, a glider. So we figured that the style of the airfoil would be better fit for sustaining stable flight. Basically, after that, I broke it down as simple as I could to figure out what the most important factors when designing the wings would be. And I figured out it would be the aspect ratio and the coefficient of drag in total. And the aspect ratio would have to be high as possible and the drag would be low as possible. So we figured that the drag would be our limiting factor, as we could sacrifice a bit of aspect ratio for a lower drag. So basically, I just played around with the numbers in Excel and found an equation for the total coefficient of drag, and set a bunch of different wingspan lengths for both the 1 foot, 2 foot, and 3 foot length for a wing. And then we had our pilot here go in and test out all the different options, see what really works, see what stayed in the air longest and what was most stable. And there we decided on making 3 foot span for both the work.
What do we gain by this? Oh, sorry, you didn't know that? Go back. Just 1 second, sir. You go back a slide.
Do that one or first?
Yes, what do we gain from these dimensions? We gained our extremely high aspect ratio to increase our L over D. We increased our time aloft, which equals more play time. More flight time means more bang for your buck. Alright.
So, as I said, it's 3 foot long. At the widest point, it's wide, 3 foot long. And so, a third of it is designed like a cockpit, and 2/3 is long. After the fuselage extends out here. And so, I was trying to reduce weight and also reduce stress. Make sure we have a high. And because you
flat and streamlined, reducing our drag. Our cockpit is leaned back in a reclined, relaxed position for our pilot. Everybody likes to relax when they're flying, right? This glider is for one person. All right, continue, please. This is you, Bob. Actually, yeah, I feel like it's like supposed to use up here. Yeah. Okay.
You guys have about 2 minutes left.
We have 2 minutes left?
Yeah.
All right, let's do this.
And I was trying to find the option to watching, but I decided to either there's different CDS or different port.
All right, next slide, please.
And this is for our take really good slide plane and either the different optical stands coefficients.
Next slide, please. Structures. All right.
All right, so I wound up doing a lot of the structures work in X-Plane itself, just I have a lot of X-Plane or experience working with X-Plane and plane makers, so I put these slots together as per Pearson's specifications. The landing gear, I decided to go with a single wheel underneath the cockpit. That's our landing gear guy hasn't done that yet, so that's what I went with because that's what most gliders use. You only really need one wheel if we're just going to have skids everywhere else pretty much. And that reduces weight and drag slightly. So the answer panel, I decided to use the standard six-pack that most general aviation aircraft use, which consists of an airspeed indicator, altitude indicator, vertical speed indicator, altimeter, direction gyro, and turn coordinator. So yeah, next slide, please. This is a picture of the instrument panel. I haven't quite added a timer yet, so I've been using the timer on my phone for the test flights, but I'll be doing that tonight. The instruments I'll be relying on are the altitude indicator, the vertical speed indicator, the airspeed indicator, and the turn coordinator. The main reason I include the turn coordinator is to basically help keep the plane coordinated in flight, because whenever you fly with a side sled, it creates a lot of unnecessary drag, and so the turn coordinator helps you prevent doing it. Next slide, please. This graph our performance characteristics numbers. Next slide, please. More numbers, more graphs, better drag. Increases with velocity, which seems a little weird, but that's what we ended up with. Next slide, please.
Our final result. We created the endurance safety goal to reduce our drag and raise our aspect ratio. Turned out with an incredible aspect ratio of around 50. 53. Our average time of flight is currently over 9 minutes of flight. The glider's so nice that even I would jump out of it.
You would not jump out of it.
No, I would jump out of it.
Oh.
Yeah. I jump out of planes regularly. Makes sense. You know. That's it.
Questions?
Yes, sir.
Do you think your aspect ratio is realistic?
To be honest, it's up there pretty high. One of the highest ones in most like high performance gliders, like the AE324 that they were talking about earlier, has an aspect ratio of 33. But we also stuck to the equation for weight based off aspect ratio and got our weight just under 3,000 pounds, which is really high for a glider, but it's still doable and it flies great. So,
what if your time allowed for us? Like this for your calculation, what was your max?
I'm not sure what we got for the thing.
We maxed out the timer.
76. Nice.
Okay, the time alone did come out a little low when we did like the actual hand calculations. It was somewhere between 350 and 400 seconds. And obviously, he proved like this line that's going to be way higher than that. We're not really sure why it came out so low. I think it's because the aspect ratio is a little unrealistic. But,
yeah. Yeah. All right, thank you.
All right, thank you, Steve.